Welcome to This Explainer. I want you to picture an incredibly detailed, high-octane 3D sci-fi arena. Two avatars slide into cover, dodging a massive barrage of glowing laser fire. Now hit freeze. If you look at any modern game engine, whether it's Unreal Engine 5 or custom Java simulator, what's actually happening underneath all those fancy 3D shaders? Well, it's all just state management and object interaction. Today, we're going to expose the code running underneath that cinematic firefight. We're going to build a combat simulator, literally from scratch. We'll start from a single line of memory allocation, scale all the way up to full object-to-object interaction, and figure out exactly how to write clean code where independent objects talk to each other without creating an unmaintainable mess. Let's dive in. So, how does an inanimate object pull its own trigger? Let's start with the absolute simplest representation of a weapon. Think of a basic gun class holding a primitive integer for bullets, let's say set to 30, and a method called fire that just decrements those bullets by 1. In our main method, we instantiate that gun and call fire. The code compiles perfectly, the ammo drops to 29, but we have a massive problem. I like to call this the ghost gun paradox. In our simulation viewport, the gun is just floating in midair, firing a bright blue laser pulse entirely on its own. But a gun is an inanimate object, right? It simply can't fire itself. It absolutely needs an actor, an entity in memory that holds it, aims it, and pulls that trigger. This maps perfectly to our system architecture. Looking at the JVM memory layout, on the left we've got our stack memory containing our main execution frame. Inside it, our variable g is holding the memory address 0x7a. Over on the right, on the heap, we can clearly see the isolated gun object existing at that exact 0x7a address. And yep, its bullets have dropped to 29. But notice what's glaringly missing here. There is absolutely no player variable anywhere in this memory state. To make our simulation realistic and actually fix this ghost gun, we've got to introduce a player and figure out how to pass this exact gun instance across our memory boundaries.
Act 2. Enter the player and passing object references.
Here's where the real magic of object-oriented architecture happens. To solve our floating gun problem, we're going to build a player class. Inside this player, we declare an instance variable, gun. Now, this is absolutely crucial to understand. This declaration is not a brand new weapon just popping into existence. Rather, it's an empty reference holder. Think of it as a blank slot capable of pointing to any gun object on the heap. Until we explicitly hand it a weapon, its default value is simply null. It's completely empty, just sitting there waiting to be assigned a real memory address. So how do we actually connect them? We write a method inside our player called pickup, and take a look at its parameter. It takes gun_g. It doesn't take an integer, it doesn't take a string, it takes an entire object reference. We wrap up our main method in 3 distinct steps. First, we allocate the gun. Second, we instantiate our player. And third, we link them together by calling p1.pickupg. At that split second of instantiation, the player's gun was null, but this pickup method bridges that gap. The crucial takeaway is understanding exactly what is traveling through that method parameter. Let's say our newly allocated gun spawned at heap address 0x999. When the pickup method is called and we pass g into it, Java absolutely does not clone the gun. No way. Instead, it passes this specific memory address, 0x999, by value. It copies that exact pointer into the parameter and then assigns it to the player's instance variable. That simple little address copy means our player now officially controls the gun on the heap. Now, this brilliantly illustrates 2 massive, game-breaking traps you've got to watch out for when passing references. Trap 1 is the dreaded null pointer exception. If you create a player and immediately try to execute p1.gun.fire before actually calling pickup, your game loop is going to instantly crash. Why? Because that reference is still null. You're literally trying to fire a weapon that doesn't exist in the player's hands yet. Then there's trap 2, which honestly is even more dangerous for your game logic, the shared reference. Imagine player 1 and player 2 both call pickup using the exact same variable g. They do not get separate weapons. Because Java just copied the memory address, they're both holding remote control references to the single gun object sitting at 0x999. If player 1 fires a shot, player 2's ammo drops too. It's a unified state, and unless you intend for 2 players to share one magical weapon, it's a massive structural bug.
Act 3. Multiplayer combat engine.
Okay, now we're expanding our player class by giving them 100 health points and a game-changing new method, shoot. Look closely at what the shoot method accepts, player target. We are passing an entire object of type player into a method of another player. This allows the calling object to literally reach out across memory addresses and directly interact with its opponent. We aren't just managing our own internal inventory anymore. We are dynamically interacting with a broader world. Inside this shoot method, two very distinct state mutations are happening at the exact same time. First, we call gun.fire. This reaches into our player's equipped weapon and mutates their internal state, dropping their ammo. Second, we execute target.hp-50. This reaches completely outside the calling player, across those memory addresses, into the external target player's instance on the heap, and literally chops their health in half. Internal state and external state, both handled efficiently in a single block of code.
Let's see how this builds in a live execution trace. Step 1. We allocate our gun with 30 bullets. Step 2. We create our players. Let's call them Alex as P1 and Bob as P2, both starting fresh with 100 HP. Step 3. We link the reference, handing the gun over to Alex. Step 4. The climax of our simulation. P1.shoot P2. Alex is the calling object, Bob is passed as the target argument. As the method executes, you can watch the synchronous updates happening right on the heap. Alex's gun flashes and ammo drops from 30 to 29. Simultaneously, Bob flashes red as his health is modified directly from 100 down to 50. We are literally watching abstract lines of code drain the health bars in our HUD.
And why this matters is entirely about memory integrity. Notice that when Alex shot Bob, Bob didn't just pass a temporary copy of his health integer into the method. He passed his true reference address on the heap. Let's say it's 0x222. Because Alex's code targeted that actual address, the change to Bob's health is permanent and instantly reflected system-wide. Anyone else looking at Bob in the game engine will immediately see him at 50 health. This is exactly how massive multiplayer games keep everyone's screen perfectly synced up.
Act 4. Core engineering takeaways.
If you take absolutely nothing else away from this explainer, remember these 3 immutable rules of object passing. Rule number 1, reference pass by value. Java is strictly pass by value, meaning it always copies the memory address pointer when you pass an object, not the underlying data itself. Rule number 2, cross-object state mutation. Because the receiver holds that true memory address, any modifications they make, like draining a target's HP, alter the actual object on the heap permanently for the rest of the application. And rule number 3, encapsulated interaction. We didn't write one massive, messy script to run this battle. The most elegant, complex software architectures emerge simply from combining self-contained objects, like gun and player, that collaborate by passing references.
So you've now mastered the foundational object interactions that power inventory systems, combat engines, and multi-actor simulations. But I want to leave you with a provocative thought as we wrap up today. If managing these simple references is how we drive a single firefight between 2 avatars, how on earth are we going to automate all this chaos and assign custom weapon loadouts when we scale up to a massive 100-player battle royale? Well, we definitely need to automate object initialization, perhaps using constructors and constructor overloading, but we'll have to tackle that massive upgrade next time. Thanks for exploring the virtual battlefield with me today. Keep experimenting with your code, and I'll catch you in the next one.